Pointer on, that'll probably help as well. Brilliant. Yes, thank you very much. So good afternoon, everyone. As introduced, I'm going to talk to you a little bit about composite materials and track, some of the work that we've done to date. As an overview, to those who attend the Wessex PWI as well, you may have seen some of these slides. I have refreshed these. I did a presentation similarly for them a few months ago now, so I've just brought that up to date. But the general overview of what I'll sort of cover is a bit of the background. So composite materials, what we're doing, why are we doing it, and what's driving that change, how we're using that within Network Rail at the moment, a little bit of the backstory about how we go about and how we have been going about approving the composites for use in track to give a bit of a better understanding for how we go through that process and sort of the intricacies that are involved in that. A little bit of an overview on the types of composites. It's not as black and white as just plastic or otherwise. And then a little bit, which is probably a bit more on the technical side. So some of the lessons learned that we've gone through on the introduction from composites. The controls framework, so some of the standards and the TWIs that people might be interested in going through. I'll go through a few of the salient points on those. But otherwise, the information is where to find that. And then some key points on that in terms of sort of maintenance considerations as well. So into the what's driving the change. So some may be aware, it's a bit old news now, I suppose. The creosote ban in July of 2021 originally sort of sparked the use of composite materials. This is more specifically around softwoods. And obviously we've been pushing that elsewhere and the use of composites elsewhere outside of composites, not just because of the creosote ban, but from all the experience that has been seen so far with composites, we do get a reduced whole life cost, as we expect the composites to last a lot longer than their timber alternatives for a start, and potentially concrete. We get improved sustainability and improved circularity and increased asset life. And here just a snapshot that I've shared, which is from our environmental strategy, which I think most people in Network Rail anyway will be quite aware of. Some quite challenging targets in terms of environmental friendliness, sustainability and circularity. And this all pushes us on that direction, that trajectory for composites. So what does that mean? I guess from a nationwide perspective, we're looking at composite materials across the board on all kinds of sort of track, all parts of the track system, I guess. More specifically, we've got the sleepers on the right-hand side, which we'll go through and people will be at least reasonably familiar with. We're using it in longitudinal bearers as well, and have been doing for quite some time. And a new one, which I will go into a little bit of detail on, is just level crossings as well. So some sustainable alternatives to the timber, but in the vast majority of cases, with the exception of this on the left-hand side on the level crossings, these are sort of nationwide acceptance now. They're easily used or relatively easily used within the restrictions of the PA, but are generally approved for use. And we're pushing forwards with our sort of strategy and direction to see where else we can start integrating this into track. In terms of product approval, for those who are sort of part of some of the central functions like technical authority might be quite familiar with this, for others maybe less so. But just to give a bit of a flavour for the process and the documentation that we go through to approve products. And for composite sleepers in particular, I just thought I'd share some of the documentation that we go through. So design for reliability is obviously a key one. This is really a sort of cradle to grave process, which is about the design manufacturing, includes all the installation, failure mode and effect analyses, really trying to get to the core of making sure the product is designed and fit for purpose from the get-go to try and give us the most reliable product as we're integrating that into track. That's something like a 40-page document for this process in particular for composite sleepers. It's you know, as the component gets more and more technical or more and more safety critical, the depth and the detail that we dive into on some of these processes becomes more and more intense, and that's sort of reflected in this. So 40-odd pages in that design for reliability. In terms of common safety method, really understanding that's more about understanding the operational risk to the infrastructure when we're introducing these novel components. So we take a good look at the operational risks, the component risk, the material, try and identify as many risks as possible. And all of those require mitigation against those risks. So we go through all of these and list them. We identify the current controls, where we might need to improve those controls, and really try and lock down and make sure what we're introducing is, again, fit for purpose. You then go into the operational trial requirements for something like composite sleepers, and sleepers in general as such an integral part of the track system. It's important to really know the performance of the product as far as we can on the paperwork side, and make sure we've bottomed out the key risks. But really, once we're integrating that into track, the level of risk or the consequence of the risk becomes a lot greater. And the operational trial for something like sleepers, which are such a big part of the track system, is a really key part in understanding some of these failure modes, understanding the bits that you can't do on paper, things like handling, installation, understanding how it's compatible with our existing operations and automation, so track relaying systems, as well as existing things like timber nips and sleeper dogs, how we work with those and how we use existing systems around sleepers. Can they still be used with these composites? And it's also about evaluating these sort of unknown unknowns, really getting to the bottom of, there's going to be a lot we don't know about plastics and about composites as a new material, and we have to try and understand as many of those as possible before we start just rolling it out nationwide and lose somewhat control of where these components are going and the vast quantity that would be being used. We need to get to the bottom of that as early as possible and make sure that it's safe both in early life and throughout its sort of journey in track. And I've sort of alluded to it in that as well, but controlling that risk at national level, obviously, once the PA is approved and we move out of this trial environment, the full product acceptance, the controlling the data and understanding and interpreting any of that data to monitor the risk at a national level becomes incredibly challenging, which, going back to things like the common safety method, makes the reversibility of that change. We lose monitoring, we lose the reversibility. And on the scale that you'd obviously install sleepers at, that's something we need to be quite careful with, but be realistic as well. We don't want to lose the opportunity of using a good component or a good product just for the sake of like overly prescriptive sort of risk analysis. We need to be quite fair with that and understand where the risk actually lies and make sure we're doing that in the proper way. So there's a lot of paperwork that sits behind that before we even move into the operational trials and the requirements. But all of that sort of stems basically from the sort of fundamental understanding of how a sleeper fits in our overall assessment in terms of engineering. So those risks and the analysis that we make before it even moves into track really stems from an understanding of where and how the sleeper interacts with everything else, which is kind of demonstrated on this slide. We need to set an environment and a system, a track system boundary, and really try and understand all of the different components and parts and the other existing system operations that feed into that, because the sleeper may be the only change, but how that interacts with everything else within that wider system compared to what the previous component might have done can be sort of some of those unknown unknowns that I talked about earlier. We can use equivalent evidence where needed. So some of the ways to mitigate some of these risks might be, as I've sort of mentioned down here, we have some existing sleeper standards, TLK 029 and 030 for wooden and concrete sleepers. We've got some equivalent evidence and similar reference systems from previous examples, such as those used in Japan and Germany, who were slightly quicker off the mark than we were for composites. Just understanding the material as well. It's a new material, but HDPE has been used and been around for a pretty long period of time. So actually understanding how that material works and how it operates, its safe limits, is all part of that. And this last point, sort of innovation giving the opportunity for system improvement. So we know that there's these opportunities to increase whole life cost, and let's try and move with that. Try and give the opportunity for this sleeper, which may reduce sort of ballast or sub-ballast degradation, may improve the conditions for the rail or the rail pad. It's about understanding that wider system concept, and understanding it's not just about the sleeper, it's about everything that goes alongside that within the track system. Another reason to go through, another part of going through the product approval that we went through for composite sleepers in particular was some product demonstrations. So I can take no credit for these photos. This was Rob McDonald who led this one in Preston. We did a number across the country to try and raise awareness of the sleepers, try and give people an opportunity to use and handle it. I kind of mentioned earlier about installation and handling, but it also gives people the opportunity to work with this different material, understand the differences, and sort of apart from having more use for the guys on site to be able to understand how and what to do with the material. It gives us a better opportunity from a product approval perspective of understanding some of the limitations and some of the material properties that we really need to understand and be able to work with. So a couple of these examples was just the amount of swarf that comes off in particularly these plastic sleepers, which is a bit of an unknown. Obviously, if we're not drilling them and we're just putting them into site, we don't get a huge amount of information off the back of that. And it's not always easy to obtain that information without actually physically doing it with our tools and our equipment. But also things like this, like screwing of the plastic. What we found when we did the trial sites was actually without doing some counter boring, the wide shank on the AS screw can cause the some of the screw holes to sort of balloon, and you get this lifting off the base plate, which doesn't then get a full sort of face contact on the sleeper. So some of this stuff is information that without actually going out and getting onto site to go and physically do these tests, we'd never understand this. And if we'd just gone ahead and installed into track, this would come out in the wash. But we want to understand those risks before we get to that stage. So we're not making sort of nationwide changes and trying to track back the issues that we may or may not have evaluated beforehand. So that goes in and that features in, and you will see sort of later on, it features in the work instructions that we've put in to better understand this and the standards, because again, it's those unknown unknowns that we don't yet, or we have to evaluate and find out about from a product perspective. There's other things like spot resleepering, which we had to do some deeper dives on. So obviously, as it's a fundamental part of what we do in track. And if you can't spot resleeper, it's a lot more limiting. Not to look at like the cost equivalence in its own right, but just understanding the stiffness and actually can you change the composites and integrate the composites with existing softwoods and hardwoods without having too much of an issue with regards to either settlement or track defects. So we had to undertake an FEM study just to understand this in a little bit more detail. What these graphs kind of show is generally in softwood and hardwood, there's not a huge amount of difference between using a composite in track and a difference in settlement between 1 in 2, 1 in 3, and 1 in 20 in softwoods. Same with hardwoods. It's a relatively small difference, but we do see quite a significant difference in terms of total settlement between like when integrating that into concrete. Sorry. So this was one of the reasons why, although we're not at that stage yet with regards to concretes, we've been able to relax some of the spot resleepering clauses which were in the original trial product acceptance, and was a concern when we first integrated the composites into track. But it just goes to show that whilst it might be safe for what we're doing at the moment, we still need to be cautious when introducing it and approaching the sort of higher track categories. And it's these kind of evaluations that all feed into that overall sort of bigger picture of making sure that what we're doing is safe and fit for purpose. I thought I'd take the opportunity to go through some of the previous concerns that we had with particularly with HDPE composite sleepers, because those are sort of the more widespread in use at the moment. And we went through a few teething problems, as you can kind of expect with some early developments in the R&D. So this in particular was taken from Sherrington Viaduct, which was one of our first sort of trial sites for the sleepers. And what you see on this this lower image is NMT data overlaid with some manual gauge measurements that we took through the Sherrington Viaduct site where it had been relayed with composite sleepers. And you see the extent of the composite sleepers, and you see the narrowing of the gauge here as we go through the composite sleeper section, which returns to normal either side of the composites. And therefore, it raised the question, rightly so, of is there something we don't know about composite sleepers? So even though we do all the belt and braces to try and make sure we get things right, it's not always perfect. And I guess this highlights the importance of running those operational trials. So we asked the question, what is it about the composite sleepers that we're not accounting for at the moment? Is this additional weight of the guardrails? Is this coefficient of expansion? HDPE is more prone to expansion and contraction over a temperature range than, say, wood or concrete would be. Is it simply incorrectly gauged? The composite sleepers are plated off-site, so the composite sleepers are plated off-site, and so were they just plated wrong? Were they plated in a different way to how timber is, or plated in the same way and this isn't appropriate? And obviously we need to understand if this is prevalent elsewhere. So because we have a limited number of trial sites whilst we're running this through, it's easy for us to go back and identify if this is a problem elsewhere. Obviously, the larger the scale of the trial, the more difficult that becomes. The top image on the right here shows a run effectively of a whole lot of NMT traces that were run through the Sherrington site, which overall showed that through the course of time, it varies very little in terms of distance between the different NMT runs, and there was no sort of specific correlation, which led us to believe that sort of fluctuating temperatures are going to make a massive impact on our gauge, and therefore gives us some peace of mind that actually it's probably not directly related to something like the coefficient of expansion, which would have been a little bit more of a concerning one. This was the one that was sort of raised. The first thing that we sort of jumped to was the thermal coefficient of expansion. And so this sort of helped to put some of those conversations to bed. As I've mentioned, that it does have a higher coefficient of expansion compared to, say, concrete and wood, and FFU, which I'll get onto in a little bit more detail, which is another type of composite. I'll talk about that later on. Like I say, within the operational temperature ranges, the thermal coefficient is greater than those others, but it's still relatively small, and that's kind of illustrated by this this plating up table, which we put together. The findings from Sherrington were ultimately that the sleepers were incorrectly plated off-site, which was raised with Syca, who are our contracted supplier at the time, and that's been closed out with a new process. As I mentioned, we've measured with NMT and Tiger data, as well as manual measurement, to confirm that there's no obvious or alarming change through the seasonal cycle. So we'd got to the bottom of the issue, and that's not really something we're concerned about specifically for sleepers, and bearers is something we're still working on. And as part of the new standard for composites, again, which I'll mention later on, we're working to understand the coefficient of expansion limits and set those to make sure that we don't introduce any problems. But from the work that we've done with the existing Syca ones, it wasn't a problem for the ones that we've introduced onto track currently. Another one that was raised during the operational trials was a fire risk. Rightly so in many ways, and the fire engineers, once hearing about HDPE sleepers and things like Grenfell in the background, raised some concerns about the use of HDPE within tunnel environments, which, as I say, is fairly understandable. It's not as clear cut as just HDPE. So the calculations that are sort of done to measure that flammability risk and the calorific content of that isn't as clear cut, because the compounds that are used in these HDPE sleepers are different to sort of the conventional, say, HDPE cladding. But we did do extensive fire testing, or I should say Syca did extensive fire testing at some laboratories. And in almost all of these categories, the HDPE does outperform the existing timber. And the overall category, which is a fire classification within the standards, is a D, A being the highest, and I can't remember the lowest, but D is pretty standard. It's the same as timber. Smoke density and ignitability far lower than timber. But we had a good debate with the fire engineers about how to apply this and how to use this, because the site was already in for HDPE, and do we go about cladding this HDPE with alternative non-flammable materials, and how do we get to the bottom and agree a way forward? And basically, it came down to using a hierarchy for sleeper fire risk in particular, where we take concretes as our sort of optimal choice, but where concrete can't be applied for various reasons, then composites do sit above timber in the overall sort of fire risk weighting. The FFU that I've mentioned briefly earlier on, and I will go into a little bit more detail of, but just for a comparison for those who do know it and will retrospectively be able to look back at this, the FFU does have a higher classification. It's a slightly different material rather than HDPE, so it sits at a classification of B. But we've still got some additional work to do on smoke toxicity and density, which need to be closed out before assuming the material like FFU would be more suitable as a composite material than HDPE. But regardless of that, at this point in time, we're contracted to use HDPE composite sleepers anyway. So it's not like it would be an option at this point in time anyway. The image on the right hand side here just shows an example of just these flame tests. So where you stick a blowtorch incredibly close to a small sample of the Cycut sleeper in this case, and immediately after the removal of the flame source, the material sort of self-extinguishes. So these are the kind of tests. It's an extensive range of testing that's done under the EN tests, but the additional tests that we undertook sort of just to highlight the sort of lack of concern, I guess, overall in the fire risk and how this has sort of changed over time. So in terms of HDPE, I've covered that in a little bit of detail, I think, but HDPE composites are currently contracted to Cycut, as I've mentioned, in Network Rail, and there's 2 PA certificates attached to that at the moment that have been completed off the back of the 12-month trial that we undertook with the sleepers. It's not all the way there yet. We've got work to do to get these sleepers up to Cat 1A, and that is, yeah, I mean, a fairly significant milestone, a big hoop to jump through at the moment. We've got some way to go yet, but we do have 2 depths. So there's two PA certs because there's 2 depths of sleepers. There's a 135mm sleeper, which is more of a shallow depth than was originally envisaged as the replacement for softwood. And that's approved up to the top of Cat 3 and 90 miles an hour. And then the second one, which is the one that we hope will be able to progressively get up to Cat 1A and 125, is currently limited at 100 miles an hour, and that's 155 mil deep, just a little bit of extra depth for various reasons, but generally high-speed sleepers tend to be between 155 and 160 mil deep. So this one has been approved by Deutsche Bahn up to 100 miles an hour, which is what gives us the confidence to run it at 100 miles an hour as well. And we will hopefully be progressing soon to some sort of trials to get that up to 125 miles an hour. I've included the certificate for interest. There are limitations on the use, and the ones that are particularly important, I think, are we state that the track category and the speed on the certificate, and there's some limitations for sleeper type mixing, which you can find in the user conditions if you're interested or you're using it. We make reference to the fact that it is now able to be used in tunnels as well. And at the moment, we're currently trying to get all the NTC and TRS, so automatic relaying systems, trialed and up and running so that we can use those in high output in the future. There's a fast clip base plate that is, well, goes alongside this 155mm one to try and hopefully get sort of high output and the sort of track relaying systems up and running with this, but it's a work in progress at the moment. And then lastly, just for anyone who would be on the call or who is going to be using these, there is a designation in INIM for these. So you can, I think it's in the process of being changed to just composite sleeper at the moment, rather than trial composite sleeper. But if installing new composite sleepers, then there is a designation to put in to specify those over wood, just to keep that traceability. I've mentioned composites a couple of times, and maybe this was something to put at the start of the slides, but generally composites is a fairly loose term when we describe sleepers and bearers. In terms of the traditional word, the traditional use of the word composite, it's not really what we use, but it's become the sort of coined phrase and term that we use for the railway in essence. So there's 2 sort of types. HDPE and the plastic composite sleepers, which I've already sort of described and we've gone through a little bit of detail on, as the most prevalent at the moment. But there's also the fibre-reinforced foamed urethane, which is FFU. So the HDPE plastic sleepers are in essence a plastic which is extrusion molded into shape. So melt down the plastic and effectively mold it into the pattern that we see. The FFU is a very different material. It's effectively a string of glass fibers, which is the length of the sleeper, which are then effectively passed through a resin, which creates the sleeper shape in essence. So it's almost dragged through a mold, which creates the FFU that you'd see at the end. So a little bit more like a fibrous and a little bit more wood-like than the traditional plastic sleepers. And that's the layup as it looks prior to getting soaked in the resin, which just gives you a bit of an idea of these sort of really long continuous glass fibers that you'd see prior to that. So that's what actually it looks like before becoming the sleeper. Moving into the realm of FFU, seeing as now onto the topic, it's been in use since early to mid 2014. And we granted it full product acceptance in 2021. This is predominantly for use in longitudinal timbers. So they have the longitudinal bearer contract, and that includes sort of cross sleeper bridge sleepers as well, not just resting on longitudinal timbers, but those which are direct fix as well. We have Newark flat crossing, which people will be aware of. I will touch in more detail. So that's a single S&C type layout. We're not quite in the S&C space overall for composites yet, but something we're working on. And I'll touch now on an alternate use, which Southern approached myself for, which was looking at alternative uses for wooden timbers. So in this particular case, level crossings. So we're replacing sort of wooden level crossings. Can we do that in FFU as an alternative material, which should in theory be longer lasting, stronger, should perform better, and improve the asset life, where especially in areas where it's particularly hard to get to, or particularly hard to get the possessions to replace. Could these be alternatives that will be longer lasting in essence? So timber is obviously a legacy item. This would be coming in as a non-legacy item. There is a level crossing standard, TRK 4040, which obviously as a new sort of level crossing material, we endeavoured to meet as far as we could possibly. There's one very difficult condition, I suppose, for both timber and for FFU, which would have been the problem. There's a thing called HB loading, which is in essence a simulated. This is an example of a single unit of HB loading, and this is basically trying to simulate vehicles passing over the crossing and understanding whether it's capable of withstanding the loading of certain category of roads, sort of primary roads, motorways and things like that, or minor roads, your lesser used sort of countryside kind of roads. So what we found was that this HB loading in particular couldn't be met without some kind of dispensation from Sekisui on those design limits and some derogation against this design loading, which is currently in the standard. This goes back to some of the engineering that's involved in the PA side of things. Baker Hicks undertook an independent design calculation for the FFU versus a traditional timber crossing, which Southern has sorted, but it reported that timber wouldn't meet the 45 HB units either. So at the very least, the material that we'd be using would exceed the requirements of timber, although not necessarily meet the requirements of, say, 4040. But that is again designed for full-scale primary road level crossings. Dedicated level crossing systems that you see from various companies out there. So what we did is we looked into the dispensation to approve the product for use on sort of minor roads, which would require only sort of 30 units of HB loading, and a derogation was put in place to approve that trial. The dispensation in particular is when you look at the overall strength of material. So we take it, say, an average value of the strength of the FFU. There's going to be some deviation depending on the material and the production outside of that to give your sort of overall average value that you can quote, and your string of deviations. You have a guaranteed value above this to which the FFU should always meet, because it's well above the highest case, the lowest case. And then you take a safety factor and you put that on to create a calculation value. So what we did was basically mitigate against the calculation value and calculate versus the guaranteed value. which was deemed safe under the calculations by Baker Hicks and by our sort of like internal process. And as this is still far in exceedance of what we should ever see as sort of the minimum value achievable by the FFU that for this grounds, and then reducing to the HB30 allowed us to sort of take those calculations and actually approve it and put it into place. The other thing that we did do as part of that was to try and include some other best practice from 4040 rather than just derogate and say it can't be reached. We tried to do some other implementations, such as this trial you can see on the right hand side, which is an anti-slip test. So as this level crossing is used by foot pedestrians as well, trying to get some approved design for how we could etch this best to ensure the water still runs off the surface, but also achieve the best non-slip that we could. So we tested a number of patterns and then applied that to the FFU. So there are limitations, obviously, to this trial, and it is still a very limited trial with only 2 sites in Southern at the moment. But with any luck, the hope is that this would then become an alternative to potentially like-for-like timber replacements. And all of these, as we specified them, the FFU is built to existing timber sizes. So we use existing, off-the-shelf timber sizes. So that in theory, this can be applied to sort of any timber like-for-like replacement. We just do the same thing, but just with FFU instead of timber. So quite a good use of the product rather than having like a custom built something like we'd use for the longitudinal bearer systems. Further in the FFU, like I say, it's the longitudinal bearer system contract they have at the moment, but FFU has sort of been proven elsewhere. They've got a pretty good track record on Shinkansen, on the bullet train in Japan. And so at the end of last year, Eastern approached me to approve the use on some high category track, try and look at some of these aging assets, again, that are difficult to get in, where we have to use wood, but are needed on these higher categories. Although FFU, again, they're not the contracted deliverer for sleepers at the moment. They've got the proven track record for Shinkansen, and the side-cut sleepers have got a bit more work to do before we get them over 100 miles an hour, and therefore need a bit more rigorous testing than the FFU at this point in time. So we agreed a small section trial of the FFU. There's a few bits and I's to dot and T's to cross in terms of PA approval. But again, I should reiterate, it's not a free issue at the moment for FFU whilst the side-cut is still in contract. But it supports the route with an aging asset, which should last longer as a result. Continued innovation on 2 material types rather than just going down a single supply route with the HDPE types. And equally, there's benefits that we know that we can get from FFU, which HDPE cannot currently achieve, and also vice versa. And there's going to be the same in reverse. So that's another sort of progress on the FFU. Ultimately, what we want to look at is a longer term strategy. And this is something that we in TA and also with support from the routes regions, route services and the supply chain are sort of working to try and deliver alongside actually the environmental team as well, is to try and put together something of a menu of sleepers. We have our existing sleepers and we take some examples here, and what we're trying to build together is a life cycle assessment and the criteria for various sleepers, which would ultimately give someone like a designer or an engineer in the route or region almost like a menu of what to choose and where. So I've taken out the actual unit rates at the moment for the purpose of showing this online. But once completed, hopefully this would include all the information which gives you the whole life cost calculations and some of the average life expectancies and the expected and average tonnages over a year in its lifetime. Obviously, there's a long road to go. The first section of this here is relatively easy to complete. The latter part here, which we've got the arrows over the top, not so easy. And at the moment, we just have categories of sort of high, medium, and low. And the objective is to try and get these a bit more quantitative rather than qualitative, which the fire and safety performance we're getting quite close to now. We're starting to be able to do these fire classifications on the back of the work that we've done with the HDPE sleepers, but better understanding of lateral resistance and the performance for lateral resistance. So these are where we've got red here. These are 2 target ones because these products aren't about yet, but these are aspirational targets. but we want to put some kind of figure against this. What is the actual lateral resistance, and what benefit does that give us in terms of reduced risk for track buckles and similar? Same thing with ballast and geometry degradation rates and stiffnesses. At the moment, very little information, and there's probably a lot of work to do in terms of the research to get to the point where you can do this. Same with circularity, but circularity is one that we are getting a lot closer to being able to put some physical values towards. It's just not yet been completed. But this is all work in the future to try and, like I say, help make this sort of menu of sleeper choices. This is currently listed to concrete, steel, hardwoods, and the composites, but there are other material types out there. There's low sulfur alternatives, low CO2 concretes that we can look at, which may reduce our overall CO2s, maybe not our circularity conversations. There's also things like graphene sleepers at the moment, which are in a lot of conversation, which are very, very early technology readiness levels, but may be part of this long-term strategy that we are sort of aspirationally aiming for. I mentioned briefly about composite bearers. It's still something that's very much under consideration. I know, obviously, we have Newark flat crossing, which you can see here, which is a very unique example of the use in S&C. Trying to apply that to composites to S&C in general with the various types and the layouts is a little bit more intricate, and so there's still some work to be done. We're considering the tendering options at the end of this year and early into next year. And hopefully some of the specification work that we've already done with composites can feed into that work, but there's still a lot of unknowns that we don't have clear-cut answers for. So work to be done, but unfortunately not there yet. Going into some of the lessons learned. So obviously it's been quite an extensive process, well, from 2014 with the FFU and more recently with the HDPE to get to where we are now. And I thought it worth sharing some of the information and some of the knowledge that we've learned along the way, which hopefully helps others introducing new materials or new products, but also gives some of the awareness to sort of the roots and regions of some of the different perspective that we have to kind of take with some of these composites. So we have FFU and we have HDPE, and both are technically composites, but they do perform very differently to one another. There will be applications where one is more appropriate than the other. For example, the FFU is significantly more expensive, but the FFU has better properties mechanical properties in a lot of different areas. So the benefits might outweigh the cost for those differences. But the HDPE is becoming the sort of standard sort of sleeper. So it's being aware of those two different types and that they do perform differently is very important. We also learned roots and regions have preferences when it comes to the different material types, which is absolutely fair enough. But for better or worse, the contracts when they were awarded are very independent. At the moment, we have HDPE and only HDPE in the sleeper side, and that is something we're looking at more closely when we come to the tender evaluations potentially next year as to whether and how we can either open the opportunity for more material types to be available to those roots and regions, or ensure there's at least choice to come out the back of that, obviously having to comply with the contracts and procurement requirements that we as a company have to adhere to within that. The important thing as well is to understand and try and shift towards this whole life cost evaluation rather than the over and upfront material costs. We know composites are more expensive to purchase upfront, and in some cases that's significantly more expensive, and in other cases it's not. But the FFU has been in track more than 40 years in Japan with a significant, with an expected service life which is realistic, so 40 to 50 years, with minimal failures, and we have a good amount of confidence that whole life cost evaluation that we can do now is realistic, and so having that sort of that forward thinking and forward looking perspective on whole life cost and not just the upfront materials is really important if this is going to be sort of grasped and taken forward. The 12-month seasonal trials were really important for us in terms of understanding these key assets. I went through the details of those previous concerns that we had, even though we'd gone through the rigorous product acceptance process, and we still found things that we didn't know about the material once it had gone into track. The product acceptance is a long process, especially for these key assets where they are an integral part of the system and a very safety critical part of that asset as well. and it becomes more challenging to do the product acceptance after we've already awarded the contract. So one thing we're doing with future works, especially with the bearer tenders and with the future sleeper tenders as well, is look at how we can do some of this work prior to awarding contracts to save the pressure that the engineers are put under by the supplier who just wants to supply something, but at the same time, we have to manage that sort of safety concern. And lastly, an important one, which sounds really obvious, but is sometimes quite tricky when dealing with suppliers in particular, is that all products will fail given a long enough time period, which sounds so blindingly obvious. But when we're working with some of the suppliers, and it's very easy to do so, is it doesn't fail like this. It won't fail. Your product will never see a failure mode, but we know it will at some given time. And if we're inspecting this and we're trying to manage this and prevent this happening, we need to know the precursors to this failure. So even though it's never been tested and it's never seen this failure, it could happen, it might happen, and we need to know what the telltale signs are for that, and actually getting that information from the suppliers in some cases, trying to get someone to point out the failures in their product is not always the easiest. And we need to consider this right from the very beginning and the get-go in order for us to give good information to the routes and regions on how to inspect and maintain these components when necessary. Falling into sort of the last little bit, I think, of my presentation, just around the controls framework. So for those of interest who don't know about it already, there is a new standard hopefully coming out later this year. That's on me. That's NRL2 TRK 039, which covers the technical requirements and performance specifications for composite materials. It is predominantly focused on suppliers and supplier requirements for FFU and plastic HDPE sleepers. But there are some bits and pieces of information that may be of use. So when that is published, if you're going to be using the composite sleepers at any point, it may be worth a little skim through if you're not part of the usual sort of standards briefing process anyway. There's two TWIs which are now live. They were briefed at the June quarterly standards briefing. This is 3C039 and 3C040, which are specifically around the FFU longitudinal bearer systems and the side-cut composite plain line sleepers. A few salient points I thought worth pointing out for the TWIs, just whilst we're on the topic of it, that I thought might be useful. But again, they're a few page documents, so if you're working with these, it's well worth having a read through the TWIs. But the 039, so the FFU particular one, the FFU does perform very similarly to wood. Pilot hole sizes are very much the same, assuming you're using the air screws. The main failure modes, which are very uncommon, are cellular collapse and indentation of the base plate, which is something you'd see on wood anyway. Material splitting or cracking, which again you would see in wood, although the intricate details of how that appears in FFU might be slightly different, and that's in the TWI. And then lastly, delamination of the material. So because of the way the fibers are run, it's a the delamination of the material is a more prevalent failure mode than say tension compression, where you might get a crack in the surface. It's more likely to split down the ends, which we've highlighted in the thing as well. We generally cut it at slower speeds, so you don't melt the material. It's sort of glass fiber and a resin in there, so there is a chance that you will either melt the material or get a whole load of goo on your equipment. So it's best to run at the slower speed to try not to melt the material, have that impact. There's specific FFU paint and quick filler types, so a spike fast alternative, of which the catalogue numbers are in the TWI. And generally, if cutting or drilling, overalls and at least FFP3 rated masks or goggles should be worn. Some people are using full respiratory, like RPE, full face masks. That's a sort of personal choice. The FFP3 rated mask should be good enough for any of the material which comes off, and also vacuums can be used to help capturing that material as it's cut for more of the sort of projects and where you're running long strings of this. And around longitudinal bearers, I guess it's a little bit more of an opportunity. 040, the main failure modes are sort of bending, warping, plastic deformations, base plate indentations, and material splitting and cracking, which are sort of fairly obvious plastic ones. Again, low likelihood, but some quite obvious ones and can be shared and are shared in the TWI. They can be purchased plated off-site as well, which helps manage the risk of this ballooning under the plate, which I discussed earlier on. we like to say with regards to the swarf, you can see the sort of the quantity that comes off. So if you are drilling it on site, ideally we collect this where possible. We need to do more in terms of logistics and how we collect and recycle this, and that is something we are looking at further within the supply chain. But where possible, just to prevent it just sitting or falling into the ballast, that should be collected where possible. Again, cutting to be done at slow speed. It is a plastic, so for the same reason, you don't want to melt the material and compromise either material or your equipment, because you'll get less life out of it. And contrary to the FFU, you can use spike fast on the side cut sleepers. I did mention as well, like I say, with regards to the plating offside, counterboring of the pilot holes is really important with this material to prevent that ballooning of the base plate surface, especially if using things like AS screws, which are the more sort of prevalent ones where this is an issue. And that's it. I think I've pretty much taken all my time, so apologies if I've overrun. But I guess any questions? Which I can't see.
No, really informative. Thanks. It was really great, Jamie. There's none in the chat, but I think I've got a hand up. Philip, I don't know if you want to come and off mute and ask your question.
I'd like to ask about critical rail temperatures in hot weather. Do composite sleepers have any, or cause you to reduce the critical rail temperature and thereby impose speed restrictions in the early because of their much reduced mass compared with concrete?
It's a good question. Not at the moment, anyway. It's not fed in. So I would say no. Ultimately, you do the same as you would do for, in essence, wood, which would be the comparable at the moment.
Okay, but wood has a penalty, doesn't it, of 7 or 9 degrees or thereabouts, I believe.
Yeah, so apply the same logic in essence. I think it's something we are still obviously looking at for more long term and understanding if that has an impact. But the actual weight of the sleepers is pretty significant still for the composites. So I think we apply the same. I think I need to double check what we've got in mod 14, I guess.
Okay,
yeah,
thank you, Jamie.
question.
Thank you for your talk. Very interesting.
No problem.
Lovely, thank you. Apologies, got your name wrong there, did the surname. Robert, you want to ask a question?
Yeah, good afternoon. Thanks for going through that. Just a couple of questions. The first one was on, I may have got this wrong, but it looked like you had a scale for which sleeper preference to use, and it looked like composite was above timber for selection in tunnels or underground. Have you had any testing or results back yet on the toxic side of it, i.e. the toxic fumes that come off when it burns? I work on London Underground, and that's one of the key failings that we're having difficulty with at the minute, is the toxic fumes that come up rather than the way in which the mass burns. So yeah, I was just curious if that was something you were going to do or have started yet.
Yeah, so it's for the HDPE, we've done it. I'd have to go back to the report because it was some months, a year ago now that I went through it. I think from memory that the toxicity was not so much of a problem with the HDPE. It is with the FFU, which is why we've granted it for use within the HDPE granted for use within the tunnels. But at the moment, FFU, which we're not using as a sleeper yet anyway, that's the one that we've got more concerns about the toxicity levels on, and we haven't done the testing for that yet. So
okay, that's lovely, thank you. One more question was just around where you're proposing or starting to use it, FFU for crossings, level crossings. I was just wondering, have you done any sort of friction testing, or what I mean by that, like sort of on the surface in which people are going to be walking across or driving across under different environment conditions? Because again, the reason I bring this up, where we've installed composite sleepers, the normal, just the normal version. Obviously, you're not meant to walk on sleepers, but some of our maintenance teams have had concerns with, obviously, when they get wet, they're more slipperier than timber. So obviously, when you mentioned about the level crossing scenario, I was just wondering if there's been any testing on that for just pedestrians, I guess.
Yeah, so we for the FFU one in particular, we have we cut the grooves in specifically based on these environmental and slip tests that are provided for like the level cross, as per the level crossing standard. Basically, you take like a rubber shoe effectively, and you kick it and you do the friction test. And we looked at a number of different patterns to see which ones gave us the higher levels of friction. The one thing which is part of the trial is to understand how long that etching in lasts, in essence, because obviously when it wears back to flat, then we've got a problem again. But as long as that holds up, then yeah, we got a good, it passed the test anyway.
That's lovely. Thanks for your time. Appreciate it.
No problem.
Thanks, Robert. We've got a question from Paul Gray. Go ahead, Paul.
Thanks, Ian. Thanks, Jamie. Really comprehensive presentation. Just wondered, and apologies if I've missed it, because I had to dive off to take a call, but is there a consideration of like a derailed wagon bouncing along the sleepers and how they perform in that, you know, very, very rare situation, but was that part of the assessment?
Yeah, so I'd have to revisit the HDPE one to know 100% from memory, but I know I'm pretty certain they've done it, and the FFU one we have as well. And we have the test results for that as well. So they do like a derailed vehicle test, in essence, like drop the vehicle wheel with a loaded mass onto the sleeper to see how it performs.
Right.
So we have got the data from that, and we were quite happy with the results.
Okay, thanks.
No problem.
Great, thanks, Paul. Brian's got a question now.
Yeah, lovely. Thanks, Jamie. And as always, good presentation. Thanks. It was a quick question. You touched on it with the track work instructions about modes of failure.
Mm-hmm.
Do we think those are likely under sort of railway conditions? Is there a sort of known? I've been watching the stuff from Japan that's 40 plus years now, but I just wonder, particularly with the HDPE, are we sort of waiting and see, or do we have an idea of what the real mode of failure or end of life will be?
Yeah, so for the FFU, very, very, very unlikely. I think the only one we've actually seen in track is in Cologne in a very tight radius curve was some cellular collapse of the material, which was kind of expected given the harshness of the conditions. But other than that, the delamination hasn't happened. They literally had to bend it to failure to get it to delaminate, and I'm talking almost half a meter of deflection.
Yeah, I was seeing some of the test results, and it wasn't what you'd normally expect in traffic.
Yeah, I think in the HDPE side, there have been some failures of splitting and cracking material, but those are generally on some of the very early HDPE sleepers used in America, where I think it's kind of understood that the mixture and the recipe for the HDPE wasn't really I say fit for purpose. I mean, it was fit for purpose, but obviously not. It's not what the current ones are today. So the bending and warping, very unlikely, but
they've got additional reinforcement, haven't they? Albeit in some of the more modern ones now, they've been sort of improved the materials with reinforcement or glass or whatever in there.
Yeah, and I think ours have got glass rather than the metal reinforcement, but the splitting and the cracking really isn't a concern with the compound that we've got anyway. They were some of the early failures, but again, the failure modes that I sort of listed, we haven't really seen in track, and that's not to say it can't happen, but what we've tried to do is be prepared to say, okay, well, this is the worst case. If something does fail on an HDPE or an FFU, this is how it's going to look, but unlikely to realistically be seen in normal operation.
Excellent. No, thanks for that. Thanks, Jamie. Cheers.
No problem. I've noted, by the way, just on the first question, Quentin, I think it was, on the CRTs that Simon's put an extract from mod 14 with respect to the material adjustments. So hopefully that's helpful.
Brilliant. Just got one more question's just come in. Excuse me for pronunciation. San Kerr, is it?
Yeah, hi. Hi. Hi, Jimmy. That was a wonderful presentation. So, I just want to know, we understand that FFU is a synthetic sleeper. So, by synthetic, does it mean it is immune to water, stagnation, drainage sort of issues, or what would be the failure mode for long-term water stagnation around is there any data about it? Yeah.
In terms of if the FFU is just sort of sat in water, would it degrade any quicker?
Correct. Or if it does, how long does it take? Do we have some data from Japan or something? Yeah.
I suppose not directly. I think it's not going to fail in the same way that, say, a timber would rot, and we may or may not see that. It's not going to be susceptible to that just because of the material in use. In terms of if you had some kind of crack and like a freeze thaw in there as like a byproduct, you'd get a domino effect, but I don't think it's really been tested on. In terms of any kind of degradation in water and stuff, it's been tested, and as far as we know and have seen based on those tests, we haven't seen any degradation. So we've got no reason to believe it would be poor in that aspect, if that makes sense. I don't know if that answers the question.
Yeah, thanks. Yeah. So it doesn't degrade the way a normal wooden sleeper would?
No, not at all. You wouldn't get any of the standard sort of rots or decays. So one of the things we do point out in the TWI is you can't use things like microprobes to detect any decay, because you don't get that in FFU. And the material, because it's effectively glass fiber and a resin that it's packed into, I wouldn't expect to see any any degradation as a result of water. And it has been tested against sort of microorganisms and stuff that might be present in sort of like biological environments such as water that show it's not degraded by that either.
Brilliant. I think that brings all our questions to an end. So can I hand over to Gareth Evans to do the vote of thanks, please?
Thank you, Ian, and Jamie, just to echo the comments from our questioners this afternoon, thank you for a really great presentation. Thank you for explaining not all composites are the same. We use the term composite, but there are some quite significant differences between the materials that you've been testing and looking at for the railway system. A really great explanation of the thoroughness of the study and the due diligence that you've been leading to make sure that when we install these in track as a safety critical product, we can all have confidence they're going to deliver what the supplier tells us they're going to deliver and give us a longer lasting, safe railway system. Really interesting to kind of see how important it's been to consider integration into all of our delivery systems as well. So for both renewals and maintenance, and the track work instructions you've issued, just to give people confidence again, inspecting the railway day to day, that they know what to look for with this new product. It's not something they should be worried about. It gives them confidence in what we're doing, and really important to have that message down to our frontline maintenance teams, so they're part of this change process. And again, lastly, I guess it's really encouraging to see how you're building on what we've learned and into our wider sleeper strategy. So giving engineers the full facts really on whole life cost, whole life carbon, performance of the product, and how it is then aligned to our design specifications in terms of material component selection. I'm sure composites are here to stay as part of our longer term railway engineering in our network and other networks in the UK. So thanks for a really great all-round top to bottom presentation on what composites means for the railway, and I'd like us all to show our appreciation in the usual way. Thank you. Well done, Jamie.
Thank you for having me on.
Jamie.
Yeah, really great presentation, and thanks for that, Gareth. Yeah, just a quick